Hello and welcome back to Physics for the 21st Century. My name is Greg Perugini, and here we are at topic number 29, simple harmonic motion. Now, with simple harmonic motion, think of it like a spring. If I was to go through time, we'd have a sinusoidal motion here, depending on where I was starting. If I was starting there, that would be sine. If I was starting up here, we'd be using cosine. And as you see here, let's follow this. Now, x equals 0, that's when the spring is at its rest position. And we pulled it here, and we're going to let it go, and it's going to have a velocity in this direction. Right? Now, you can see here it's moving here, and it's going to crunch it together, and then you're going to have a point where the total force of the spring has slowed it down to a point where it has no velocity, and then it presses it and begins to speed in the other direction. So it's going to oscillate back and forth, back and forth. Now, we could have a damping factor in this. We're not going to deal with that at this level of physics. Assume no damping. Newton's first law, without friction, this is going to go on forever like this, right? And if we model it where it's moving on the x-axis through time, you could see we have this bouncing up and down. And this period here is in seconds. A is the amplitude. And this is a positive amplitude and a negative amplitude. And we have a few factors we need to keep into account here. That the period is 1 over the frequency. The frequency is in hertz. How frequent this happens, how often, or how quickly, I should say, through time this moves. So, simple harmonic motion, if I start it at that cosine level, we have this general form of an equation. So if I'm doing simple harmonic motion, and I give you something that is 2.4 cosine of 5t, you should be able to fairly quickly tell me what is the amplitude. Well, you just match. And the amplitude, of course, is 2.4. What is omega? It's rads per second velocity rotationally. Or I should say over the curve. Better way to put it. That is also equal to 2 pi times the frequency, by the way. And in this case, it is what? 5. So I can easily get the frequency, right, is equal to 5 divided by 2 pi, or 2.5 pi. And of course, since I know that t equals 1 over f, I can get the time. So with these equations, given that I'm going to we have this standard format for simple harmonic motion. Often you see it just as initials, SHM. You can gain a lot of information. Now, to find the speed at any given time, I would take the first derivative of this equation. And that's going to lead me to that point. Well, if I go to that point now, you could see that for our particular equation, it's going to be a negative a 2.4 times rads per second, which in our case is 5, times sine of 5t. There's our equation for our example of simple harmonic motion. And to get acceleration, we're going to take the next derivative. And what's that lead us to? Negative 2.4 times 5 squared times cosine of 5t. So I have stepped through from the position to the velocity to the acceleration. And if asked at t equal 4 seconds, what is its position? What is its velocity? What is its acceleration? You should be able to give that for me. Make sure, since we're using a rads per second radian calculation in your sine or cosine, you want to make sure your calculator is in radian mode. So we could also find a point where we have the maximum velocity and velocity max is, looking back at that equation, is going to be rads per second, its radial velocity, times the amplitude, and the acceleration max, omega squared times the amplitude. Now we could also, there's a couple of other equations you want to keep a note of, and one of them is t equals 2 pi mass over k, where k is the spring constant, sometimes called the force constant, depends on your spring. And of course then that leads you to frequency is 1 over 2 pi square root of k over m, inverse of that. I did already mention, of course, that t is equal to 1 over f, and that that omega is equal to 2 pi times the frequency. So you need to know your way around that as well. Okay. Let's do an example here. We have a spring that's oscillating in simple harmonic motion by the equation now. Notice we're saying that it could be oscillating up and down if the spring was attached to a ceiling, whatever. We're just saying it's oscillating in the x direction. We have no friction. And we're starting right at the cosine level. There is no phase differential. Sometimes you'll see that they'll ask you for a phase in other books, and in this book as well. But at this level of physics, I don't think it's necessary. All we're saying is that with phase, instead of starting and doing that, we're starting maybe somewhere around there or so, where we're out of phase. You'll get more of that in the second semester when you talk about interference between waves. Right now we're going to say we're in phase. We don't have to worry about a phase constant there. So we have the spring and it's doing that. So we can ask the question, what is the frequency? What is the period? What is the rads per second? What is the amplitude? Okay. And those are easy questions, right? Given the standard format for simple harmonic motion, 4 rads per second, 12. Frequency. Well, frequency, I know that frequency, that omega is equal to 2 pi times the frequency. And so if I know that omega is equal to 12, frequency then is just 12 divided by 2 pi, right? 1.91 hertz. And of course the inverse of that, 1 over 1.91, approximately 0.52 seconds. Fair enough. And so that's fairly straightforward, right? Just pulling that out. But if I asked at 2 seconds, at a specific period of time, right? What is its position? Well, then it would be 4 cosine of 24, 1.7 meters. Velocity at 2 seconds, negative 4 times 12. Remember that equation where you had negative amplitude times omega, sine of 24, right? We took the first derivative to get to this point. That's going to lead me to what? You can do that calculation. 43.47 meters per second. Again, make sure you're in rad mode when we're doing this, right? Acceleration at 2 seconds. Well, if you remember back to what I had written out, that this would be negative 4 times 12 squared cosine of 24. Negative 244 meters per second squared. And of course you can do velocity max. 12 times 4, 48. Acceleration max is 12 squared times 4, based on just plugging in what we had before, 576 meters per second squared. So I'm going to go back a slide here so you can see what I'm talking about. All we did was, given the standard format, I could pick out what the amplitude is and what omega is, and I was able to calculate here the frequency, the time, the rads per second, and the amplitude are just plugged from the equation. Taking the next derivative, I can get the velocity, again plugging into this equation, getting the answer here, and taking the next derivative using this equation for amplitude and rads per second, plugging that in and getting this answer. Again, making sure your calculator is in rad mode. So, given a particle moving in simple harmonic motion and these equations, you can derive all these variables. Don't worry about phase difference in angle for the moment. Make sure your calculator is in radian mode and do the practice problems that you would find online or in the book. So, that's simple harmonic motion in a nutshell. Good luck.